Hi everyone, welcome to this explainer video on memory management. Today we will explore how operating system handle memory behind the scenes. This topic is very important and essential for both system programming and application design because how memory is managed affects speed, efficiency and reliability. So here's what we will going to cover. First of all, we will talk about why memory management is so important and we will use a real life analogy to understand it. Then we will explore memory hierarchy from super fast registers to slow hard disk. Next, we will compare memory allocation strategies like static and dynamic. Next, we will go deeper into concepts like paging, segmentation, virtual memory, garbage collection, and then we will discuss fragmentation and along with its types, internal and external, both. Then we will end up with a case study on Linux for this memory management. So let's begin with why memory management is important. So for understanding this, let's take an example. Imagine your memory is like your study desk. When your desk is clean and everything is organized, you can work quickly. Books are at your fingertips. But just if your desk is messy, cluttered, and overloaded, you spend more time searching than studying. This is exactly how it works in computers. Memory management makes sure that data is placed where it can be accessed quickly and efficiently. When it's not managed well, the program slow down, either it crashes or run out of memory. Just like in real life, being organized makes everything smoother. So from here on, we are going to discuss our next topic, memory hierarchy. So what memory? It isn't a big chunk itself. It's actually a hierarchy of different types of memories, which is stacked like a pyramid. Just at the top of the pyramid lies the registers. Very tiny but extremely fast. They're the fastest type of memory. If we want to access the data quickly, the register is preferred. Cache. Cache stores the frequently accessed data L1, L2, and sometimes L3. Still fast but slightly bigger. Then comes the RAM, our main memory. It's larger, slower, and used for active data. And at the bottom of the pyramid is our secondary storage, SSDs and hard disk. Much slower, but they hold more data. So the thing is, higher up the pyramid, the faster the memory, but also more expensive and smaller in size. While at the bottom of the pyramid, it's slower, it's less expensive, but it holds more data. Operating system is responsible for shifting data between these all layers. So now our next topic we are going to discuss, that is allocation strategies. Basically, there are two ways to allocate a memory. First is static allocation and another is dynamic allocation. From the name itself, it is clear that static happens at compile time, while dynamic happens at runtime. In the static allocation, variables are assigned memory before the program even runs. It happens all at the compile time. This is very simple, this is fast enough and safe. But it lacks one thing, that is flexibility. You can change once it starts running. While in dynamic allocation, on the other hand, it happens at runtime. So it's more flexible. You can use what you need, but it requires careful management. For example, if we forget to release memory, we get memory leaks. If we access memory that's already freed, it can crash your program. So it's a trade-off between control and safety. Both have their uses. One is used at compile time and one is used at runtime. If we want more flexibility, we use dynamic allocation. If we want it to be fast, over flexible, then we use static allocation. So moving forward, we are going to discuss our next topic in memory management, that is paging and segmentation. To make memory more manageable, operating system divides it into blocks. So there are two ways, paging and segmentation. First of all, we are going to discuss what is paging. It splits into equal size pages. The program doesn't need to worry about where are those pages goes. It just uses them. But sometimes the needed data isn't in memory. This causes a page fault, and the OS must bring the data from disk. It's slow and costly. But at segmentation, the another concept of it divides the process, it divides the memory into segments. So it divides those segments into it divides the memory into logical sections, code, stack, heap, etc. It gives more structure but can lead to gaps in memory. And that's where where the problems arise of fragmentation. So we are going to discuss in our upcoming slides and its types. So here we are we have discussed what is paging, what is segmentation, what is page fault, and what are the advantages of segmentation. As segmentation is used for logical division of memory, while the paging simplifies the memory allocation. From now on, we will move forward to another important topic, that is virtual memory. Virtual memory is like a clever trick. It's kind of when programs pretend that they have access to more memory than physically exists. It's a kind of simulation. So what operating system does, it maps virtual addresses, which is used by the program, to physical addresses, real memory location. Physical addresses are real memory location, while virtual addresses, which is used by the program. So it maps the virtual addresses and physical addresses using something we call MMU, Memory Management Unit. This mapping is stored in page tables. The page tables are includes this mapping between virtual addresses and physical addresses. If memory runs out, less used data is moved to disk temporary for a temporary period. That's what we call swapping. This makes the multitasking possible. Many programs can run as if it has its own memory space. They are isolated and safe. It's a very key feature uh, operating system uses. So here we get clear about the logical address, which is used by the program, the physical address, which is real memory locations, and the address translation, which we get by the page tables, and the mapping is done in page tables, and memory management unit, which is responsible for mapping logical addresses and physical addresses. Next, we are going to see the garbage collection. In some programming languages, memory is automatically cleaned up for you. This is called garbage collection. Just take an example. If something is not in use, you replace it with something which is going to be useful. So there are similarly here also, it's a form of automatic memory management. It will free up the memory space so that new process can take the space. There are two popular methods we use, mark and sweep method. The mark does finds everything still in use and deletes the rest. The sweep deletes the rest. It's safe, but it can cause pauses during cleanup. Another method is reference counting. Reference counting, it deletes the data when no variables point to it anymore. It's fast, but it cannot handle circular references. For example, language like Java, Python, they use garbage collection. while C and C++ they leave memory management up to the programmer. So from now on we are going to see our next important topic which we have seen, fragmentation memory management. As programs run, memory becomes fragmented. There are two types of fragmentation occurs in memory management. First is internal fragmentation and another one is external fragmentation. So internal fragmentation it occurs when we reserve more memory than needed, while external fragmentation happens when small gaps appear between allocated blocks. It will make it hard to fit large chunks later. So, in a simple language, we can understand it by internal fragmentation is the memory is allocated but it is not in use. While external fragmentation is there are some unallocated blocks, uh, there are some allocated blocks, and between them there are the gaps which is not in use for the large chunks, for the large data. It's like having lot of tiny empty drawers but no space for a big book. To fix this, operating system uses techniques like compaction, memory pools, slab allocation. It will reducing the fragmentation, keeps the memory more efficient and stable. So we have discussed a fragmentation in memory management. Now we are going to see our, our case study on Linux memory handling. How Linux handles the memory. Let's look at how it uses a system called Buddy Allocator. Memory is split into blocks of size 2 to the power n. If a block is very big, it's split into buddies. If buddies are freed, they merge back. This helps balances the speed and memory efficiency. It also uses C groups, that is control groups. As you can see in the slide, it will manage how much memory each process or container can use. That's how servers can run many apps safely. If the memory runs out, the OOM killer selects which process to terminate to free space. Linux system is efficient, flexible, and battle tested. So, at the end, to wrap it up, we will conclude it with memory is a layered resource, and managing it well is a key to efficiency, better efficiency, performance. And we have discussed static and dynamic allocation, and there are different use cases where static is used and where dynamic is preferred. Understanding virtual memory, what is garbage collection, with example also, the fragmentation and its types and how it happens. What's the difference between internal and external fragmentation? We have discussed it all, and it sums up our memory management topic. So I hope it gets clear smoothly. Thank you.